Hello everyone and welcome to this presentation. In this analysis, we are going to be conducting data preprocessing. So we are going to do various steps, data preprocessing steps. We are going to apply those steps in our data to ensure that at the end of this preprocessing is that we have a cleaned data that can be applicable, or we can use that data to build um, for modeling purposes, build a machine learning model on top of that data. We do need to ensure that we have clean, consistent data to ensure that whatever results we are going to present or whatever outcomes we need to infer from the data, we need to be as certain as possible. That is the main reason as to why we need to make sure that we have cleaned data that is good for such a task. So for this preprocessing, these are the different steps that we will be conducting for this data. So we first convert the data type of variables which are misclassified, and then we can remove the duplicates, the unique as well as the zero variance variables in case we do have those in our data. Then we can also do an outlier treatment. So as you can see, we have three options that we can choose from. But in this case, we are going to apply all three. Then we can decide which one is best for us to use. In terms of the missing value treatment, again, you can see we have three steps that we can take, or some three options that we can do under the missing value treatment. Then after we are done with that, we are going to step 7 and 8 will be all about removing the highly correlated variables in our data. Okay, so when we try to build a model from our data, then we don't need these highly correlated variables because they are of similar importance. So to ensure that we save on computation resources, then we just need to work with the necessary variables in our data. So basically, that's what we are going to be doing under the data preprocessing steps. So these are the steps that we will be doing under that under the data preprocessing. So I'm going to take you through to now the data preprocessing under the Jupyter notebook. So I'm using a Jupyter notebook, and this is where I will be taking you through the various data preprocessing steps. So actually, this one is where we are actually doing the actual processes. Then at the end, we might draw some conclusions about which steps we are going to be using them going forward. Okay? So the first thing, as usual, is all about importing the necessary libraries. So these are the libraries that we are going to be using. So as you can see, we have the pandas, the NumPy for matrix manipulation. These three are for data visualization. And I just want to suppress any warnings that might arise. So that's why I'm using this. So I'm going to execute this cell so that we are able to import these libraries. So after this, then the next step is all about us loading our data to our data frame. So I'm using the read CSV function so that and pass in the file path. Then I'm just using the head method to try and print out the first 5 rows of the data. This is the data. Once you have an output like this, that means that you have successfully imported the data onto your the Jupyter notebook. Then I'll use the df.info just to print some information about more information about the data that we are handling in this analysis. So you can see we are getting information about the number of entries. This can be regarded also as the number of rows in our data. So you can see we have a total of 25,000 rows in our data, and we have a total of 111 entries, or consider this as the columns. You can see the different data types for the values under the respective columns. So we have a total of 80 columns that are of float 64, and a total of 31 columns that are of int 64. So those are the the data types, the column, and the number of rows in our data frame. So the first instruction is all about converting the data types to of the variables. But you can see already we do have we can see that all our columns are being represented by these data types. But to explicitly confirm this, maybe when you are going to do some other data preprocessing steps or data manipulation steps, you might alter these data types. So to explicitly suppress this, you can just use such a loop to specifically assign the data types for those columns in your data. So with this, maybe to prevent further alteration of those data types. Then from that, so we're just creating a loop, then selecting the data types, include float and this in the respective columns. Then if the column data type is this, so we're just going to affix float 64. If it's in 64, we're going to affix this one here. So there's nothing much about this because already our data was in the correct data types, if I may say that. Okay, so we don't have any categorical column, so that one will be unnecessary for us at this moment. The next step is all about checking for duplicates. So we don't want to work with data that has duplicates because it might constitute our results or our output. So we need to check for those duplicates, and I'm using this function, the duplicated method, to check for the duplicates. Inside the brackets, you can see I'm using keep equals false. This means that we are just going to sum all the duplicated rows in our data frame. Then if the duplicated rows are greater than 0, that means we do indeed have duplicated rows in our data. Then we can just print your data set as this duplicated rows, the count. That means the count. Or else you can just print this, and when I execute this, you can see that we don't have a duplicated rows in our data. So we move on to the next step. So the next step is all about removing unique value variables. So this step is also important. These variables are often, the unique value variables are also known as the constant columns. And the reason as to why we are removing those is because they do not provide any meaningful information for analysis. That's why because they don't vary across the different rows, so their value in our data frame is irrelevant. So we need to remove that sort of columns. To do that, I'm using this, creating something like a for loop to look inside our the columns in our data. Then I'm using the nUnique function to check for the unique values under those columns. Then after that, we can drop them. Then we can maybe print the columns that were removed to see which columns were removed. So no columns with unique values were found in our data. Okay, that's okay. Again, we are going to repeat the same thing, but in this case, we are going to be removing zero variance variables. These columns, again, they do not vary at all, and they do not provide useful information for data analysis. Again, the same thing as how we applied previously, it's just the same thing. This one is for the zero variance column. This is for the unique value column. So a zero variance, then I remove these columns. Okay. So I'm going again to execute this to see if we're going to get columns with zero variance. Okay. So I'm going to execute this again, and you can see that no columns with zero variance was found. Okay. So the next thing is all about, I'm just offering a little bit explanation about the zero variance variables and the unique value variables. So I've already explained what these two mean. So an example of a column where the For example, if you have a column where the value is 1 for all rows, that represent a zero variance variable, and unique value variables, for example, this one include like the social security number, product ID, if you have phone numbers, okay, ID, phone numbers, product ID, emails, so things like those fall under the unique value variable. So you can work to remove those values. Also, another thing is, can you use one or both of these? For the zero variance variables, this should always be removed because they provide no variability or information. But for the unique value variables, then this one you might consider leaving them behind. For example, if you want to do processes like merging data sets along these unique variables. So if you want to merge a data set according to, let's say, social security number, if you're handling a data like that, with the product ID, something like that, then you need to include these variables in your data so that for the merging process is successful. So after that, the next thing is all about outlier treatment. So we are going to remove outliers in our data. So before we start removing the outliers, we can plot either a histogram also as well as a box plot just to visualize the distribution of data in those columns and maybe to visualize if we do have outliers in those columns. So the histograms will be specifically for checking the data distribution. So for this case, I'm suppressing if we are going to, if any warning will arise from this. Then I'm selecting the column between 20 and 40. Then it should be a column with a numeric variable. Then I'm defining a grid layout. So for the chart, it will be 4 rows and 5 columns. Then flatten the axis of the array for easier iteration. Then you use this for loop with the enumerate function to plot the histograms. Then after that, we can hide the empty subplots. Then after that, we can just display our chart. So when we execute this, mind you, it's going to take some time, but we'll just be patient and wait for it. Here we're taking zero variance. Okay, so let's see if, okay, we do have our chart at the moment. So this is the chart. So you can see how the different, the distribution of values under the different columns. So you can see, for example, histogram s7.new.rev.p3p6. This, you can see this is almost attaining that normal curve, but it's not ideal because of we do have some outliers, I think so, that are causing this shape. But most of these columns, you can see that they are not respecting that normal curve. So we do have a lot of outliers to remove. So for this, to check for these outliers, then we can use now the box plot to check for these outliers. So you can visually check for these outliers using the box plot. Again, from the box plot, so if you do understand the box plot, then these points falling outside the whiskers, they do represent the outliers present in the different variables. So we do have a strong case or a justification as to why we need to drop these outliers. Just from the look of things, you can see that indeed we do need to drop these outliers. So while dropping these outliers, we are provided we can use 3 techniques for this case. The first one is all about the box plot. Okay? So I've provided an explanation. So a box plot is ideal if your data is a non-normal distribution or skewed data, such as this one here. As we do have a data that is skewed, so you can apply the box plot for that. And box plot, essentially, we are using the interquartile ranges, which finds the lower and the upper bounds to identify the outliers. Then for this case, any value that is 1.5%, 1.5 times above or below these thresholds, then we are going to identify those as outliers. Then the next step will be all about removing those values. So I'm not going to interfere with the original data. That's why I'm creating a copy of the original data frame. Then I'm specifying the quartile ranges, then calculating the interquartile range. Then this will calculate the bound. So you said 1.5 times the IQR, which is the interquartile range. Then we identify the outliers using this method, this for loop. Then we can, the next thing, can combine all outlier indices into a single set. For outliers in outliers boxplot, values, outliers, I think this one is will be the indices into a single set. Then after that, we can then count the number of rows before removing the outliers. Okay, so that we have a count of before and after removing the outliers. Then we can remove the rows containing the outliers. So we use the drop function, index outliers. So this one we are grouping outlier indices into a single set. So those rows that are considered as outliers, so we are grouping those together. Then we are using this to drop function to remove those columns. Then we count the number of rows after removing outliers. Then we can print a summary of that. This summary is very important because you need to know how many columns you are actually removing in your data frame. So you can compare this with the other approaches to see maybe one type of outlier removal is removing almost all of your data. For example, for this one, you can see the number of rows after removing outliers. We are only remaining with the 5,032 columns. We are removing almost, you can say, almost 90% of the rows are removed using the boxplot with the this interquartile range. Of course, you might tweak this. Quartile ranges. For example, you can say 15% and 85%. Okay? So it all depends. So you might again can see when we change the interquartile ranges, you can see that we are remaining the rows after removing the outliers. You can see this one here. The number of rows removed, you can see there is a significant change. So you might play around with the interquartile ranges. By that, it will can be a little bit lenient. So as reducing to 25 and 85 quartiles, and then we are a little bit lenient. From that, we can see that now the number of rows after removing, they have significantly increased. Okay, so you can play around with the interquartile ranges to actually do that. So let's also another thing is that we can try something with this. After removing these outliers, then maybe we can plot the box plot, but we can change our data. We can use this as our new data. This is the reason as to why I didn't want to interfere with the original data frame. Okay, so that at least you are flexible. You can compare the different type approaches. So this one I'm going to compare again after removing the outliers. So you can see we are trying to make some improvement after changing this to this. So you can see there's some slight improvement when you compare this and this. You can see we are trying. So you can play around with this. Earlier on it was 25. 25 and 70, 75. So if we execute this and this again to see that, so if you are very strict, you can see again we are trying to achieve something there. Anyway, so let me use the 15 and around 85. I think that one is a little bit fair. So the next thing is all about the standardization. For the standardization, again, This is ideal for normally distributed data or when wanting to assess outliers based on the standard deviation and the mean. So for normally distributed data, then I think this approach is quite conducive. Again, I'm creating a copy of the data frame. Then we can create the mean and the standard deviation for each numeric column, as you can see. Then I calculate the bounds of the outliers using the 3 sigma rule. So this is the mean. So essentially, we are multiplying 3 with the standard deviation. Then we subtract the mean. And for the upper bound is the mean plus this calculation. Then we identify our outliers, combine all outlier indices into a single set. Then we count the number of before removing outliers, remove outliers, then do the same. Okay. So after removing this one you can see that this is the number of rows that were removed, and this is the number of rows after removing the outliers. So I can run this code again. So I can just copy this and then paste it here so that we can visualize those columns within, as I said, we are dealing with the columns between 20 and 40. So I'm going to execute this with the same data. Then we can see how it is working with respect to this. Okay, so I don't see there is some difference. Anyway, so that's it. So this is how you can correct that or visualize that. So the next thing is about capping and flooding. So the quantile-based flooding and capping is a technique where outliers are managed by setting the values below a certain lower percentile, for example, the 10th percentile and the 90th percentile. So again, these values you can play around depending on the data or on what you prefer. So again, we said the lower percentile is this and the upper percentile is this. So we are putting caps for that. Then we count the number of rows before removing the data frame. Then this is how we remove our class based on the quantile threshold. Okay, so the lower value is the data for column in select the data types, do number in this in the columns. So quantile, lower percentile, upper percentile, like that. Then we identify the rows to remove using this. Then we can remove the identified rows, count the number of rows after removing, then we can print this. So it's just as simple as that. Then again, from here, you can see that the number of rows that we're removing, number of rows before, number of rows after removing, and you can see we are quite removing a lot of rows in our data frame. Again, you can maybe play around with this, and if you do so, you're able to get different values for that. You can see the number of, now you can see we're only remaining with 19 values, 19 rows after removing the outliers. So again, I think this one is, among the three, this one is very strict. This one is very strict. Then I will select this one if we indeed had normally distributed data, but in this case we don't have a normally distributed data. So the most appropriate technique to use for this analysis, I will use the Boxplot. Then I will just vary the quartile ranges just to ensure that I'm not losing a lot of data, and then I'm a little bit lenient in terms of the outliers, so that I have enough data to try to build a model upon that. Okay, so I think by that we are done with how to check for the outlier treatment. Let's move to 6, which is about missing value treatment. With this, checking for missing values. So we're going to check for the missing values. The first thing is to track if any missing values are found. So missing values false. Then you're going to loop through each column in the data frame to see if missing value count then is null. Using the is null function method, then we sum the null values. And if missing value is greater than 0, then we print the column has missing values. And then missing value found true. Okay, then that means we found the missing values. If not, you can just print this statement indicating that our data set does not contain missing values. So and actually that is the case. So your data set does not have any missing values. So that's it. Either way, you might find that it's not that in all cases that you will have data that does not contain missing values. Some cases you'll have data that has missing values. So we're just going to apply the different techniques that we are provided so that we can deal with that. So in case in future, if you encounter a problem that that requires you to remove records with not available, so NaNs, then if it's less than 5, remove the records with this. So this is the what you will use. Again, I'm just creating a copy of the original data frame and I'm working with that. I don't want to interfere with that. Okay, then I can see we didn't have a missing value, so we expect that we're not going to remove any rows or columns in our data. Remove if less than 50. Again, the same thing. And just use the same thing. So with this code, is that we are calculating the threshold for not available percentage. So not available threshold length of the data times 0.05. This is about 5%. Then we are using the drop to drop that using the thresh. Using the thresh, I think the thresh technique. Then we are going to apply that so that we are able to drop those columns. So the threshold, this one here, and threshold are calculated based on the number of rows in the data. So you can see this is calculated based on the number of rows in the data. Then from here, we are going to remove rows where the number of not available values is less than the threshold, 5%. This one here, so you can see just doing the same. Then the in place is equals to true. This modifies the data frame data directly without needing to reassign it into a new variable, something like that. Okay. And now we can print this to see how many rows or columns that you dropped. The same thing I think applies here. It's not something different. Then after we drop our columns, then the next step is all about imputing with mean median for the either numeric and the mode for the categorical values. Again, don't think we are copying creating a new data frame and copying data from our original data frame. So in case our data you are going to input for the numeric column. So for the numeric columns, you can use the median or the mode. So here, let me just add if mean use something like this. Okay. So for columns in data select, so we are selecting columns that contain a number as a data type. Then we are checking to see if the columns indeed contain any missing value. Okay. So we are going to check using the isNull method. Then calculate the median or the mean if you're using the mean. So for this case, we are trying with the median. Then after that, we are going to fill the missing values with the median or the mean if you're using that value for those respective columns. For the categorical column, again, we are selecting columns with object as a data frame, as a data type. Then after that, we are going to do the same thing. Check if the columns has a missing value using the isNull method. Then after that, calculate the mode. So the mode essentially means the most frequent value in those columns. And then we find the most frequent value. And then we populate that column with the most, fill the missing values in that column using the most frequent value. Then we don't think we didn't have missing values. But anyway, if you execute this, you can you'll see the before and the after. So before, if for example we had missing values, maybe our entities won't be 25,000. After missing the values, imputing the values, then you could find 25,000. The next thing is about dealing with the highly correlated variables in our data. So with this, the first thing that I saw that will be necessary for us is try to print out the correlation matrix. So from the correlation matrix, we are able to get a general picture of how our values are indeed correlating. So even though we are dealing with a lot of values, we are able to get such a correlation matrix. And this correlation matrix has this something like a scale ranging between negative from -1 up to 1, 0 being the middle. And the color ranges are able to tell you how these values are correlating. So if it is almost red, then we have a high correlation. And if it is negative, again, you can see we have a negative correlation, but in the opposite direction. So with this chart, we are able to see how our values are indeed correlating with each other. So we can see some areas are having this almost red color. So those features are highly correlating. So again, through this visual outlook of the correlation matrix, then it gives us a strong case that some of our values in our column are highly correlated. So we need to drop those columns before we proceed. So we are provided with two techniques that we can use. The first one is the correlation matrix. So in the first case, we calculate the correlation matrix. And this computes the pairwise correlation coefficients between all numeric columns in the data frame. And the reason as to why we are using the this one, ABS, this method absolute, this is to take the absolute values for these coefficients. So whether they are negative or positive, regardless of that, we're just going to make sure that those values are positive. Okay. Then we set a threshold for correlation coefficient. So in my case, I've set that to be 0.9. You can use 0.8, 0.7, depends. This value is adjustable. It's not something that is written on a stone. So you can adjust these values depending with your requirements. So for my case, I'm using a 0.9. Then I've also specified that you can adjust this value. Then you find the upper triangle for the correlation matrix. So with this, I'm using, when you see this thing, don't worry about it. So in the correlation matrix, you can see we have this triangle. So we have this diagonal that you can see it is red, and we have this upper triangle. So what I'm just doing in this line in code is to select the upper triangle and not the triangle, the below triangle. Okay. So this is to render this as irrelevant with that. So this one is just to create a Boolean mask of the upper triangle of the correlation matrix. So we are keeping that, making that, only selecting that. Then the correlation matrix where this one applies the mask to correlation matrix, thereby converting the values outside the upper triangle to be n, so not a number. Okay. Then after that, we need to identify columns to drop based on the correlation threshold. So we are using that for columns in the upper columns. If any column is greater than the threshold, then we drop those columns. Then we can just print our output for that. And then from this, we are able to see df.info. We're able to see that after applying this correlation matrix and sorting that and dropping those highly correlated columns, we can see we are only dropping about 51 columns, and the remaining is a total of 60 columns. So after doing that, the correlation, applying that, I can see we are only remaining with 60 columns in our data frame. Okay, that's it. So that's how you can tackle this challenge. And again, this number is all this depends on this threshold. This threshold is adjustable, so we can adjust it depending on the requirements based on the data that you are dealing with. Then after that, I think the last thing is about multicollinearity using the variance inflection factor. So the first thing is that I'm importing the variance inflation factor module. I did not import it earlier. Then we can store the initial number of columns in our data frame. That means is that again we are going to drop some columns. Then I will do the before and after so that we're able to see which how the number of columns that we are remaining with. Okay. Then the function, creating a function to calculate the variance inflection factor for each feature. So this is the function for that. We initialize the variance inflection factor data frame. Then after that, what we do is measure how the variance of the reflection of the regression coefficient is inflated due to multicollinearity. So that one is by using whatever I've said is along this one. Then after that, we can iteratively calculate the VIF and remove features with high VIF. So getting a method for that. So threshold we have specified is 5. So according to our instruction, you can see this one is 5. Then after that, we need now to calculate VIF, high VIF. Then it should be if the column has a high VIF that is greater than the threshold. Then if not high VIF, then we include a break statement. Then if that column is if the column is not having a high VIF column, then I think it won't initiate this break statement. So that means we are not going to drop that column. So after doing that, it's going to, this is something like an iterative loop that we are creating here. So we're creating something like an iterative loop. So it will going to check for each column in our data. Okay, it's checking for the high VIF. Okay, so if the high VIF columns, if it is not having a high variance inflection factor, then if not, then you're not going to break. But if it has a high, then we are going to drop that column. So drop columns with high VIF factor. Then we are returning our DF. Then remove features with high VIF. Then using our the method that we created up here, then we are applying that to our data frame. Then from there we print our results. When we print our results, this one it takes a lot of our calculations. Then after that, I think we are going to print the number of columns before checking for multicollinearity. Then we are going to check after checking for multicollinearity. Then we check the length of the columns after that. Then from there we can able to deduce how many columns that are remaining. Runtime warning. I think actually this problem might so it's taking some time, so we need just to be patient. Again, with the variance inflection factor, we're going to iteratively remove the we're going to iteratively remove features with a VIF greater than the specified threshold, and this threshold we said is 5. Again, this value is not cast on stone. Okay, so this value can be changed, so you can adjust this variance inflection factor to suit your needs. So the number of columns before multicollinearity is this. So the number of columns after checking for multicollinearity is this. So we're only remaining the 12 columns after checking for multicollinearity. So I think we have now reached the end of the data preprocessing. So these are the steps that you can conduct given a sample data to do the preprocessing steps to ensure that your data is clean and consistent and ready for other applications such as building machine learning models on top of such data. So we have undergone, we have done a series of steps. And in this case, I just wanted to make sure that I'm not leaving those different steps out. So with this, then we are able to select the best preprocessing steps. So with more focus, for example, when we look at the outlier removal, so we can select one technique because I don't think it is advisable to apply all these techniques for removing the outliers. So for this case, we can select the Boxplot, remove the outliers, and then for the missing values, I think you can use, for the missing values, I don't think there's any difference, but you can use, because I think one deals with the number of rows, another one deals with the number of columns, and then imputation, that means imputation is necessary because you might be working with the data with the missing values. Then for correlation again, you might select maybe if you adjust the VIF factor, then you might because 12 we are really removing a lot of columns from this from our data frame, which might not be suitable. Okay, but all in all, these are the how you can conduct such an analysis, conducting the preprocessing steps to clean your data. So that's it. That's it with these steps. Then upon you now to select the best one to proceed on with your with the next step after doing the data preprocessing. Okay, that's it. That's it from my side. And